Good afternoon. Thanks for coming. I'm Andy Swanson. I work there in the Air Vehicles Directorate of the Air Force Research Laboratory right here at Wright-Patterson Air Force Base. Today I'm going to talk to you a little bit, real briefly, about some of the activities that we have going in the Air Force for developing responsive space access. We have some of the same needs that certainly this organization does for transporting large masses of material into orbit or beyond. And in some cases for us, just briefly into space as we transition to some other portion of the globe. Next slide, please. Can you forward them for me? Thanks. We actually have a variety of needs for flying at very high velocities, hypersonically or in excess of 5 times the speed of sound. Space access just being the one of them, the top one shown there. We also have plans to cruise at hypersonic speeds for extended periods of time, as shown in the middle vehicle there. And then we have another need in certain cases to boost some vehicles up where they will then glide at very high velocities, seeing some of the same types of environments that you're going to see for the space access vehicle. But anytime you have very high speed flight through some portion of the atmosphere, you have a very extreme environment. We have tremendous heating, certainly on the vehicle, very high acoustic loads, this dynamic excitation of the secondary structures, which can be very damaging, particularly when the power plant is on, whether it's a rocket or a scramjet. And then, of course, we have high flight loads as these vehicles maneuver. The wings and the control surfaces can take some very excessive loads. So a big portion of this presentation then would be talking about the advanced materials and structures that are required to meet these performance requirements in this harsh environment. For space access, they have developed within the Air Force these sets, or this set of requirements. We're looking to turn around the vehicles in a very short period of time. We can't take the weeks or months that it takes in the civilian agency to turn around a vehicle, kind of the baseline now with the space shuttle. We're also looking to lower the costs tremendously, increase the reliability, be able to fly in all weather conditions as the commandos out there in the field need a space asset or a payload delivered. We have to respond quickly. We can't wait for a nice sunny day 3 months down the road. Also looking to get these vehicles to fly many missions before they are retired, and also the subsystems. And you can see in the near term we have certain requirements that start to tighten up as we move to the right off to the far term, with turnaround times that we hope to get as short as 4 hours. Seems like quite a dream considering that it takes something like 4 to 9 months to turn around a space shuttle. But really I think due to the way we're going to build these vehicles and some of the aspects of them, I think we're very close to reaching at least the near-term goals, as I'm going to show you some of the technology we have to support that statement. Next, please. This is what we have to deal with today. Deeply buried inside all that infrastructure there is a space shuttle down there in Florida getting inspected, maintained, repaired, prepared for a second flight there. A lot of people buried inside all that grid work there. We have to get away from that type of scenario to the point where just a few personnel can turn the vehicle around very rapidly. All right, next. So there are a variety of different options for getting things into orbit. First off, something that we use today quite a bit are these expendable vehicles, and certainly there are improvements that you can be made on those types. There's also fully reusable, kind of the ultimate dream that we have, eventually get to a point where both stages or a single stage vehicle will be fully reusable. But then there's also a partly reusable system, and as you'll see here in a moment, that's kind of the way we're looking to go. With you have one stage might be fully reusable, another stage expendable. There are quite a few factors that drive you to one solution versus the other: cost, reliability, reusability versus expendability. mass fraction margins, etc. And then, of course, there is certain infrastructure factors that you have to take into account. We have certainly invested quite a bit in the launch complexes and such, and they may or may not be valid for the various concepts, such as a horizontal takeoff and landing. These launch complexes may not be what it takes. Next slide, please. So here's the kind of the scenario that we're looking at right now. Stole this slide from the Space and Missiles Systems Center. And the leading concept right now for the Air Force is to have a hybrid or a partially reusable system. Here we have a fully reusable booster that will launch up to a certain altitude and at a fairly high Mach number, touching on the hypersonic regime. There we would stage and launch off the expendable system that would head on up to orbit. Then the reusable booster would turn around, rocket back, or glide back, or maybe even have turbine engines that pop out or what have you, come back to a horizontal landing at the launch site. So there are certain drivers here: performance, reliability, cost reduction that we think we can hit fairly well. We have potential of some significant cost reductions, quick turnaround time, at least of the booster, and flexible basing, as a system like this might be able to be put into operation in more than just the two launch sites we have with the Cape and Vandenberg. Next, please. Here are some of the factors that certainly point us towards this solution. We're looking at an unmanned system, which, as you can see here, makes a big portion of this explanation for pursuing this particular solution. The thermal protection system on the space shuttle, tens of thousands of tiles that need to be inspected, maintained, repaired between each flight. We're looking at a much smaller vehicle, just the booster only, without the human capsule on it. We think we can knock the number of components down tremendously, to the point where just take maybe tens of man-hours to turn them around. And I'm going to show you some of the other technologies that help us drive that down even further. And then as you go to a non-space system, there are various subsystems that we can eliminate, and that improves our turnaround time. And as I said, no crew. We get to eliminate all the crew support. Looking at some engine development that allows us to increase the margin so that we're not operating these engines to the maximum of their capability. And this should allow a greater lifetime for these engines and allow us some reusability. So there's quite a few things we can do in this reusable booster system that can drive us to the responsive space access that we're looking for. Next, please. So moving on to some of the thermal structures, the area that, the specific area that I work in. Unfortunately, what we have found is that there's not just one thermal protection system component that we can apply to a whole vehicle and just improve upon that and get all the performance that we need. We need to look at a variety of different technologies. As you can see here, the various types of components, as the temperature capability of them goes up, so do the cost and the weight. I don't have cost numbers here, but you can see some of the weight points on these. And the most efficient vehicle you want to keep certainly at the lowest weight. That allows you a lot more payload, and it can be very expensive to have the orbiter portion. Any excess weight there, it drives your booster sometimes like a 10-to-1 ratio. So it can be very expensive. So we take the lowest temperature capable components and drive them up to their maximum before we start adding on the next component. You'll see the leeward surfaces certainly cooler. The space shuttle has these felt materials over much of those parts. It's kind of interesting that the shuttle in many places is actually soft and kind of squishy with this the felt material. So we drive that up to 700 or 1,000 degrees, and then we go up to the blankets, and then the tiles, and the carbon-carbon. Carbon-carbon, a very durable material, but very expensive and somewhat heavy, so you can't just normally make a whole vehicle out of that type of material. So next slide. There are other constraints that we have to look at. There's certain volume constraints on certain portions of the vehicle, like the control surfaces. We don't have this volume that's necessary to put thick tiles on to protect those from the thermal environment. So in those cases, we might look at a hot structure, as certainly we see in certain vehicles that are flying today. There's interior access. If we get our thermal protection system components to be ultimately durable, where there is no damage, there is a strong need to still remove and replace these, or some of these components, to get interior access for inspection, maintenance, repair of hydraulic systems, antennas, that sort of thing. There's quite a few locations on the space shuttle that they have to remove and replace these components after every mission, even if there is no damage on the components. And then we certainly have other issues such as durability due to the ice that comes off, sheds off the external tank on the shuttle. And when they land horizontally, you may have runway debris, and for military systems, we may be launching through some rain or ice particles that can certainly cause a lot of damage. Next. So there in the Air Force, we are following this approach. First off, we have to come up with leading edge solutions, and I'll describe the problem there. Then we want to improve the durability, the strength and the resistance to damage of our components, improve the operability, the ability to remove and replace them very quickly. We'd like to increase the temperature of the substructure. The space shuttle has an aluminum substructure that can not exceed 350 degrees, and that's only when it's in an unloaded condition back on the ground, which we have found for these types of structures, it's the maximum temperature that you hit is actually once the vehicle has landed, at least for these types of vehicles like the shuttle that come down and heat up very rapidly for a short period of time. The soak back actually occurs so that the maximum temperature is after the vehicle has landed, and fortunately there's no or less loads on the structure, and it can withstand 350 degrees. But we'd like to raise that 350 on up, and I'll show you a slide on that later. And then in far term, we're looking at these hot structure solutions. Next, please. The leading edges, the space shuttle has an effective concept for the leading edge that has a fairly large volume behind this, this very blunt, large radius wing that allows some cross radiation. So the stagnation point, or the very forward portion of that leading edge, heats up the most, and it kind of radiates back into this open volume, lowering the temperature so that it can withstand multiple flights. It doesn't overtemp the material. Well, for these smaller vehicles that we're looking at for the military, we don't have that large volume back there. We have to find another way to draw the energy away, or that stagnation point will exceed the reuse temperature of any known usable material. So we're looking at passive and active methods of pulling that energy away. What you'll find is that as the radius goes down here in this term, that the heat flux goes up fairly dramatically, and can certainly cause problems. We need to have this small radius to reduce the drag, and as I said, the vehicles are going to be fairly small. Transport the energy away. We've got to protect the wing, keep it from overheating. All right. You can see one concept we have there in our test laboratory being evaluated at some very high heat impingement levels. Next, please. So we have, in addition to the smaller radii, we also have some aggressive trajectories, and that we may be looking at quite a bit more cross range than what we typically use on the space shuttle. As maneuvering off to land at alternate bases and such, that can really stress the thermal protection of the vehicle. So what we're looking at is high conductivity carbon-based composites that draw the thermal energy away from the stagnation point, allow it to cool. We can actually lower the temperature here a few hundred degrees, which really can make the difference.